Understanding interest rates. This is Chapter 5, Part 3, following on the learning outcomes. After going through this presentation, students will be able to compare and contrast present and future values of constant cash flows, extending the discussion from annuities in the previous video, and distinguish between different loan types by the nature of repayments. So we'll be able to analyze these loans and understand which of them is good from a lender's perspective and which of them is good from a borrower's perspective. Later on, we'll also compare and contrast different compounding periods, talk about annual percentage rate and effective annual rate, and even APY as we hear it from banks these days. So let's find out some intuitive applications of present value and future value. So in the first situation here, we're going to take a look at multiple cash flows in which we're going to look at future value of $100 invested today, available after 20 years until the 19th year. So these are invested up to 19th year, and then they'll be available at they'll be invested at t equals 0, 1, 2, 3 through 19, and the rates of interest would be 1 to 10%. So let us go to Excel. In Excel, let us make this a little large. So 0 equals 0 plus 1, and then copy that, Control G, A 20, 23, and paste, Control V, remove that extra cell. Now here we enter the rates of interest, so 1% equals this plus 1, nope, plus 1%, yeah, and then copy that, go to the column K and paste it. Alright, we're ready now. So equals the present value, so it's 100 divided by 1 plus rate. So that's going to be $1. As we go to the right, we want to make it C, but we want to keep that 1 as it is, to the power of, now the cell that contains 20th year is A22. We have to fix it completely. So $A $22 minus $A2, and so what's happening is we are trying to discount it. $100 is available at the end of the 20th year. What is its present value today? And that is 81.95, and all now we need to do is just completely use it for all the years, yep, and all the rates. Shift Control 1. What is this giving us? So as you can see, as we approach closer to the 20th year, the value, present value, this is only going to travel for 1 year. That's why it has to be very high to be able to reach 100. On the other hand, this 81.95 can travel through 1, 2, 3, 4, 5 to 19 periods, and it will be able to reach a value of $100. Essentially what this is it's you're trying to find out the present value of an annuity due, which is available at end of each year, of $100 constant cash flows. So first let's add these up. So this is the sum total of all the present values. So this is the present value of all the cash flows, and now we can actually use a present value formula. So the rate will be at the top, 1%, comma, the number of periods is 19, comma, the payment is minus 100, comma, future value is 0, and type is 0. Sorry, 20 periods. And then Control R, because the cells are not fixed. So you have to fix $A22, $1 is fine. Control R, Shift Control 1, Control R, Shift Control 1, and there we go. All the values are matching. Now we can actually plot this as well. To see what we get out of the plot is the present value against the number of periods. So as you can see, if we start off with $81, we'll be able to reach $100 in 20 years. We have to start with a slightly larger sum to be able to reach $100, so on and so forth. At the end of the 19th year, we need to start with $99 to reach $100 at the end of 1 year. Now, on the other hand, we can also add another series here. Select data, add. The series name could be 10%, just another extreme. The X values could be the number of years, and the Y value would be all these present values that we find. And the curve is much more broad. But you look at this present value today, we just need to start with barely $15 to be able to reach $100 in 20 years. Again, the same thing though, it converges to that $95 value, because now we need to start with $91 to be able to reach $100 in 1 year. The only advantage this orange line has, it has the power of a bigger rate of interest. So we can populate all these intermediate rates in between to get a graph like this. So this is the future value. We did the present value. So let's go to the present value. Here we go. That's the present value. So the present value of all of these available, as you can see. So as the rate goes up, we just need to start with smaller and smaller amount to reach $100 in 20 years. So that's this graph. Now let's go to the future value graph. That is even more interesting. So I'm just going to modify this graph here. So instead of using present values, we're going to do the present future values. So equals 100. Actually, not to just times. So future value of $100 available today. How much does it run in the remaining 20 years? So it's going to run for all 20 years. It's going to become huge. That's exactly what it's telling us. So what all we're going to do now is copy this and paste it. So now what's happening is my $100 starting at 0 times 0 will really attain a large value as compared to, let me remove the orange line for just a little bit. So we can see my $100 starting at time t equals 0 will run up to $122 in 20 years. But my $100 starting at 19th year will barely reach 101 in 1 year. So that has a shorter time frame to run as compared to the first $100. Extending this conversation to a higher rate. Now if our rate is higher, 10%, our $100 today will really blow up to $672 in 10 years. But $100 in 19 years will have only 1 year to run, so will only become 110 in that 10 years. Now for here we have to use a future value formula. Instead of PV, we have to use an FV. And then we have to use FV A21. Nope. Sum total of all the future values. FV. What is happening here? Let's think about it. So future value of 0, 0. Oh, it's annuity due. It starts with today, right? So it's annuity due. There we go. Annuity due. The end of the time period consideration. And all we have to do is instead of 0, make it 1 to get the same future value. Because the cash flows start at t equals 0. That's why it's an annuity due. See? It started at t equals 0. So what we've been able to do is find out the future value using a formula and find out the future value using the future value function. The only thing that's different is the type. Alright. So that gives us this graph. The lowest one is the lowest rate of interest. The highest one is the highest rate of interest, and also the left hand side tells us that it is going to run the longest amount of time, and therefore it gives us the highest value. Alright, so this is the table given to you in PowerPoint. If interested, you can download it and easily use it. Alright, let's move on. So now let's move on our discussion to loans. There are different types of loans we can have in real life, and let's look at them. So the idea of a loan is we borrow the money today and repay it at the end of a certain period. So the cash flows look like this. If we borrow the money, our cash flows are positive today, and if we return it, so at the end, then our cash flows would be negative. On the other hand, if we lend the money today, then our cash flow today would be negative, and if we receive the money at the end, the cash flow at the end would be positive. So as a lender, the cash flow would be negative today and positive at the end of the loan, assuming no intermediate payments. Now that's not always true, so it's a tight assumption that we are making. Now why are there intermediate payments? They could come from interest, a combination of interest and principal, or just principal. So we will be reviewing all of those at the end. So sometimes there are some loans in which there are just interest payments with in such a way that all the payments completely expire by the end of the loan, and so no payment is required at the end. There are some loans in which there is no payment made until the very end. These are called discount loans. And then like I said, there are some loans in which we just pay the interest and repay the principal and one last interest at the end. And then amortized loans are ones in which we pay interest and some principal as we go along, not to have any value left at the maturity of the loan. So we're going to see them with some examples and calculations. So if that narrative intimidated you, don't worry, because we're going to study them with some numbers here. So let's assume Alex D has a firm that wants to borrow $10,000 for 10 years. So the loan value is $10,000, and this cash flow would be positive for Alex D initially and negative at the end by the end of the 10 years. He approaches banker Mr. Boris, who offers him 4 different plans. Now for Mr. Boris and his bank, the cash flow would be negative today, and then cash flow would be positive later on, unless he makes an additional loan to Mr. Alex. So the loan plans are as follows. Discount loan is the one in which everything has to be paid at the end, principal and interest. Constant payment loan, or constant just interest only loan, in which is one in which interest is paid, and then in the end principal is repaid in total. And then there is a constant payment loan in which the payments are such that some principal and all the interest is paid as we go along, in order for that loan to completely become zero towards the end. And then there's a constant principal loan in which the loan is broken down into pieces, and then the equal pieces, so equal pieces are paid off as we go along with the interest that is accrued. So let's look at the numbers behind these loans now. So we need to analyze and compare these plans and tell which one of them is more expensive from a lender's perspective and which one of them is more expensive from a borrower's perspective. Now, there is no right or wrong loan. It's just dependent on the needs of the person who wants to lend and the person who wants to borrow, or the entity who wants to lend and the entity that wants to borrow. So in finance, there are no right or wrong answers per se, but we need to understand from a borrower's perspective, there are some loans which are good, and from a lender's perspective, there are some other loans which are good. Okay, let's go to a discount loan. So in a discount loan, we need to borrow the $10,000. The rate of interest is 5%, and let's use this table. So I'm going to do Alt V Z 0. That cell with 5% is fixed. Actually, I can do Alt V Z Alt C 225% to make it slightly bigger. At the beginning of time t equals 0, there is nothing. The interest is calculated as beginning balance times this cell I have is B1, so fix it, $B $1. The ending balance, because it's a new loan that is started at time t equals 0, is going to be 10,000. And since it's a new loan for a borrower like Alex D, the payment that we have is we received the loan, so it's positive 10,000. All right. Now, at time t equals 1, so one period has passed. My ending balance was $10,000. That's going to accrue some interest on it. So how do you accrue the interest? You just multiply the beginning balance times the rate. So by the end of the first period, I need to make a payment. but I don't, it's a all at the end loan, right? So it's a discount loan. So I make no payment, it's 0. And therefore my ending balance is beginning balance. So end of period 1, I have $10,500. Beginning of period 2 is at 10,500. Now I'm just doing Control D, Control D, Control D, and Control D. And so you can see the interest is now growing because the initial beginning balance is growing. All we need to do is Control C, copy, and paste it. Now what's happening here is the interest is ballooning up and into 6,288.9. So what we need to do is pay it all off in the end. So minus, it's negative because we're paying it, this, the beginning balance, minus the interest accrued by the end of that period. And what we forgot to include was a payment. So if we see this plus the payment that we make, Control D, Control D, no payments are being made. So it's going to grow and grow and grow until we pay it all off, when it becomes 0. So the important thing to learn here is that we had to pay the $16,288.9 at the end of the loan at the end of the 10th year, which is what we got in this slide. So this table can be created anytime. Let's move on to the constant interest or interest only loan. So what if we just want to pay interest? So again, we can use this. So 0 equals this times, fix it, $B, $17. Ending balance is beginning balance. No, actually no. Ending balance is in beginning of this first period or end of the 0th period. We borrowed the 10,000, and it's a positive inflow for Mr. Alex D. And so the next period's beginning balance would be the previous period's ending balance. Interest accrued would now start accruing, and the ending balance therefore is a sum total equals this plus this. So beginning balance plus interest minus the payment. So if the payment is minus the interest, remember this is interest only, so you paid off the interest. Oh, plus, let's make it plus because minus of minus is plus. So again repeating, so beginning balance plus interest minus payment, so minus of 500 becomes 10,000 again. All we got to do is repeat those steps until we reach the maturity. So copy that and let's go to the maturity, the 10th period. Here is the 10th period. Now in the 10th period we're repaying the entire loan, so it has to be minus of 10,000, and voila, the value is 0 again. So we paid 5,500, 500, 500 all along until we reach 10,500. So that's exactly what we have here. The interest, we don't let it grow at all, not compound interest. We just, it's like simple interest. We just pay the interest off every period to keep the principal the same. So that is the interest or constant interest loan, interest only loan. Moving on, now this is the most fun loan, the amortized loan. So to see this, again, the beginning balance is 0, interest is this times $B, $34, and then ending balance is 10,000, and the payment that we receive is 10,000. All right, now the next beginning balance at the end of period 1 is the ending balance. There's an interest accrued of 500, so the ending balance will be this plus any payments made. What is the payment we make? Now that's the fun part. You use a PMT function. Treat this as annuity, a constant payment that will completely remove the loan by the end of the 10th year. So what is the rate for that? $B, $34. That is the rate. Number of periods. This is in the cell here. So $B, $47. That is the number of periods. Future present value. Present value is minus $E, $37. Yep. Note how we are fixing all the cells, because the payment that is calculated is based on the initial value of the loan at a certain fixed rate for a certain fixed number of periods. Future value is going to be 0 when the loan is repaid. Nothing is left. And the type is 0, end of the period consideration. So this constant payment will be made every year from year 1 through year 10. There's the amortized loan, which is very commonly used for us when we repay our house or car. So now we've accrued some, yes, so this has to be negative. Sorry, so let's make this minus PMT, otherwise the loan will just grow. So shift control 1, control D, control D, control D, control D, control D, slow fun. And so you can see the loan balance has gone down thanks to the payment we made. Interest accrued will go down as well. And the final sum, that ending balance, has gone down further. So this is called the amortization of loan. We are slowly reducing the value of the loan as we proceed. The best part is this 0 that we get at the end of the 10 period. It's not magical because the PMT function was meant to calculate this payment in such a way that the final balance would be 0 with the help of this constant payment. The constant payment is 1295.05 measured in that green cell here, which we calculated using the PMT function. Alright, so that's the same thing that we got here, 1295.05. The last loan is a constant principal loan. Now notice how what we've done here is, let's just do it. So here is the table for principal, constant principal. 0 equals this times $B, $50. Ending balance is 10,000. The payment that we receive, because it's a loan, is 10,000. The beginning balance at the end of the period 1 is obtained from the ending balance in the previous period. And then what we do is sum the beginning balance, interest, and the payment to get an ending balance. What's happening here is this $10,000 has been divided into these 10 constant payments. 10, the number, is coming from here. That's the life of the loan. So what we're doing here is equals $E, the value of the loan, $53, divided by $B, $63, not pound, $B, $63. So we're dividing the 10,000 by 10 to get $1,000. So we're part paying the loan every year along with the interest that we accrued. So the interest that we accrued was $500, so we're going to pay that off. So this is a constant principal and interest loan. Now once this happens, our new balance will become lower, the interest accrued will become smaller, the ending balance will grow but not at the same pace anymore. So you can see the ending balance is reducing at a constant value. All we got to do now is just copy paste it. So by the time we reach the 10th period, we will magically get our 0 again. So I'm going to use yellow for consistency here. So we got magically 0 again. But notice how the payments are seemingly not constant because the interest is continuously decreasing. And this is a very popular option among corporations. They like to pay off a part of the principal, a constant part of the principal, along with whatever the interest that was accrued until that time. So that's what we see here. So you can see the payment is actually reducing because of the interest going down, but the principal that's being repaid is $1,000, a constant amount. That is a fourth type of loan. Now we need to compare. So what I've been doing all along is I've been keeping a track of these numbers. What is the annual payment? The annual payment in discount loan is 0. The annual payment in interest only loan is the interest, $500. The annual payment in the amortized loan is the PMT that we calculated. And the annual payment in the constant principal and interest loan, the loan taken by corporates, is variable. Now to find out the total interest paid, we just simply add the column on the interest paid for each of the 4 loans. So we use that for the first loan, use that for the second loan, use that for the third loan, and use that for the fourth loan. There. So we just added the interest column entries for each loan. And then principal paid in each case is constant. And the total repayment is simply this since it's negative minus this plus the interest paid. This is a total payment. So the total payment made in each case is this. Well, since the principal repaid is constant, the total payment is a function of total interest. So if we paid higher interest, then we paid total repayment as greater amount. And we can see the highest amount that we paid in interest is discount loans. So if you're thinking about taking an instant loan at the friendly neighborhood discount retail outlet, don't do that, because you're paying up the highest interest. The total repayment is really high as compared to interest only. Interest only is still higher. Amortized is one of the lowest, as is the constant principal. So you can see why constant principal actually is a popular loan among corporations. But the amortized loan is the most popular among retail customers because they like that payment to be constant. Constant principal does not have a constant payment, but constant principal. The interest dollars keep changing as we move forward in time. That's why it's not very attractive for retail customers. For corporations, they have an accounting department which constantly advises them to pay that amount. So that is how we compare these loans. So obviously the most popular one is amortized amongst retail, and sometimes it's constant principal amongst corporations. To conclude, discount loans are very expensive. These are usually the payday loans and end up paying very high interest rates. The advantage of this is the money is available instantly. But however, these days, personal loans offer lower rates of interest and are also available online. The paperwork for that is relatively less, but there's a credit check. Best are constant principal and interest loans, but infeasible for retail customers. And amortized loans, the constant payment loans, are kind of similar to these constant principal loans, but more popular because they're constant. And in the amortized loan, we discussed the payment function, which we've been discussing so far in the context of annuities. And so the payment function and its arguments are used for the amortized loans. That's chapter 5, part 2. Thank you for listening.